Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs, and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness, illuminated only by headlamps, drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells, where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames mean sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins, electrorefining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electrorefining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel-cobalt-manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.
Every year, the world cranks out over 100 million cubic meters of medium-density fiberboard. That's such a massive amount that you could build a road around the entire planet with it, every single year. Imagine this. What was once trash, sawdust, wood chips, and scrap paper, is now transformed into a material worth over $25 billion. China controls half of the entire volume, while Europe and the US add millions of cubic meters each year. But what's really going on behind the factory walls, where wood dust goes from being waste to perfectly smooth panels? If you stick around to the end, you'll learn a secret that's usually kept hidden. The foundation for medium-density fiberboard isn't whole logs, but what used to be considered rubbish: sawdust, wood chips, offcuts, and even old scrap paper. It's a triumph of smart resource use. These mountains of wood waste are brought to the plant and first get a thorough cleaning. Powerful magnets pull out any metal contaminants, nails, staples, while screening systems remove sand and stones that could damage the expensive equipment. After that, the raw material goes into a huge vat where it's washed and steamed with hot steam. This isn't for cleanliness. It's done to soften the lignin, the natural glue that holds the wood fibers together. Now comes the most important step, the one that separates medium-density fiberboard from its rougher cousin, particle board. The prepared, softened wood chips are fed into a machine called a defibrator, or refiner. Imagine 2 giant metal plates, like millstones, spinning towards each other at enormous speed. On their surfaces is a complex pattern of sharp ridges and grooves. The wood mass gets caught between these discs, and they literally comb it apart into its tiniest components, tearing it into individual wood fibers. This isn't shavings anymore. It's something like a fluffy, moist cotton or wood flour. We've just deconstructed the wood down to its basic building blocks. Next, this fibrous mass needs to be dried. But it has to be done very quickly before the fibers start to stick together. So they're blown into a long, hot tube dryer. A stream of hot air picks up the fibers, and as they fly through this tube, all the excess moisture evaporates from them. And right here, while the fibers are still hot and flying in this whirlwind, the next key stage happens: resonation. A fine mist of a binding agent is sprayed into the airstream through special nozzles. This is urea resin, our glue. This mist envelops every tiny fiber, coating it with a thin, sticky film. It's a very efficient method that guarantees a perfectly even distribution of the glue. Now this resin-soaked, dry, and light as fluff mass is ready to become a board. It goes into a forming machine. The stream of fibers settles onto a wide, moving conveyor, forming a thick, fluffy, and perfectly uniform mat. Special rollers slightly compact it, and giant knives cut off pieces of the required length. It's already starting to look like a future board, but for now, it's just a thick, soft mattress of wood fluff. And now comes the climax: hot pressing. This fluffy mat rolls into a giant press. This can be either a multi-opening press that squeezes a whole stack of boards at once, or a continuous press that looks like giant moving tracks. And here, our mat is hit by two powerful forces at the same time. First, colossal pressure. The press plates squeeze our fluffy mattress with hundreds of tons of force, reducing its thickness several times and squeezing out all the air. The wood fibers are pressed tightly against each other, forming an incredibly dense structure. Second, a high temperature of 400 degrees Fahrenheit. That's 200 Celsius. This heat does two things. It activates the resin, causing it to polymerize and permanently glue the fibers into a single solid block. And at the same time, it evaporates any remaining moisture, which escapes from the board as hissing steam. After a few minutes in this steel embrace, the fluffy mat transforms into a hard, dense, perfectly flat, and still very hot board of medium density fiberboard. After the press, the hot boards can't just be stacked. They need to be cooled to relieve internal stresses. They're placed in a special fan cooler, which looks like a giant filing cabinet, where they slowly cool while being fanned with air. Once the boards have cooled, it's time to give them a finished look. First, they're stacked in high piles and left to rest for a few days. This stabilizes their internal structure. Then, each board goes through a sanding machine. Imagine a giant belt sander with several heads. Wide abrasive belts remove a thin surface layer from both sides, bringing the board to a perfectly precise thickness, for example, 16 or 18 millimeters, and creating that famous smooth as paper surface. And the final touch, cutting. Huge saws cut the large industrial boards into standard commercial formats. After this, each batch goes through strict quality control. Its density, strength, thickness, and surface quality are checked. The finished, perfectly smooth boards are labeled, packaged, and sent to furniture factories, where they will become the foundation for elegant and stylish items in our homes, silently demonstrating the noble path that ordinary wood dust can travel. The global market for medium-density fiberboard is a giant machine that turns over more than $25 billion a year. And this machine has no plans of stopping. Forecasts say it will grow by 6% every year. That means the demand for this smooth material is just insane. So who's the head chef in this kitchen? The undisputed king is China. It produces over 50% of all the medium-density fiberboard in the world. But Europe is no slouch either, with powerful players like Germany, Poland, and Turkey producing millions of cubic meters of high-quality board. Now for the volume. Every year, about 100 million cubic meters of medium-density fiberboard are produced worldwide. That number is so huge, it's impossible to imagine. Let's try. Picture a road. If you took all that medium-density fiberboard and built a road 10 meters wide and 25 centimeters thick, you could wrap that road around our entire planet at the equator every single year. It's an endless stream of material being turned into furniture, doors, and panels for our homes. Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1,800 degrees Fahrenheit, 1,000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a micro crack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer green skin and inner nodes. leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family, Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Imagine this. Hidden right under your feet could be a mountain of old car tires. You'd think it's just rubbish, left to rot in a landfill for centuries. But what if I told you that this black rubber gets a second life and becomes the foundation for modern sports stadiums? Every single football field uses up to 40,000 tires. Now, multiply that by the more than 13,000 arenas in the US alone, and you get hundreds of millions of old treads, transformed from the road into a green carpet for athletes. How exactly new life is born from dirty scraps? We're about to break it down, step by step. Stick around till the end, and you'll uncover a secret most people never even thought to look for. So today, we're heading to a cemetery. A car tire cemetery. Acres of land piled high with mountains of black rubber rings. These are the silent veterans of the road, having done their thousands of miles, now lying here, seemingly useless. But this isn't the end of their story. It's just the beginning of their amazing reincarnation. We'll follow how these worn-out, dirty pieces of rubber go through a series of brutal, yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. This is the story of how the roar of the road turns into the quiet whisper under an athlete's feet. Americans have learned to give a second life to the vast majority of tires. The recycling rate for old tires in the US is now over 85%. That's one of the highest rates for any consumer product. That means over 250 million tires a year dodge the landfill and are sent off for a new life. Some of them are burned as highly efficient fuel, some are used in civil engineering, but a significant and growing number are turned into that very same crumb rubber. In this tire cemetery, a machine that looks like a steel Tyrannosaurus Rex is at work. This is an industrial shredder. A huge loader grabs a whole handful of old tires and dumps them into the machine's steel jaws. Inside, two massive shafts with thick, sharp hooks spin with a deafening screech. They grab the tires with relentless force and, with an incredible crack, tear them to pieces. There's nothing delicate about it. The shredder's job is simply to break the tire's integrity, turning it into rough, palm-sized chunks. At this moment, the first important liberation occurs. Inside, every tire is a steel cord, a strong frame of steel wire. As the tire is torn apart, this cord is released, turning into a shiny web of steel threads mixed with rubber chunks. This chaotic mix of rubber and steel moves along a conveyor belt. And here, a powerful, massive industrial magnet spinning above the stream of shredded material comes into play. Like a fridge magnet, but a million times stronger, it pulls all the steel threads from the rubber mass. With a screech and a clatter, the steel cord sticks to the magnet and is dropped into a separate container. This steel will later be sent off to be melted down, while our cleaned rubber continues its journey. But it's still too big and coarse. The next stop is the granulator. This is something like an angry coffee grinder the size of a car. Inside, sharp blades spin at enormous speed, chopping the large chunks into a smaller fraction, about the size of a fingernail. During this process, another component of the tire is released, the textile cord. These are nylon or polyester fibers that gave the tire extra strength. These light, fluffy fibers need to be removed. To do this, the rubber granules pass through a system of vibrating screens and air separators. Powerful streams of air literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have a clean, but still quite large material. To become the surface of a stadium, it needs to be turned into a crumb. For this, the granules are sent for final grinding, often in what are called cracker mills. These are two massive grooved steel rollers that rotate towards each other at different speeds. The rubber granules, falling between them, are not so much cut as they are torn and ground into the tiniest particles. As a result of this process, we finally get what this was all about: crumb rubber. It's a uniform, free-flowing mass, like black caviar or coarse sand, where each particle is only a few millimeters in size. This crumb is carefully sifted to ensure a perfectly uniform size, and is packed into huge 1-ton bags. Its journey from a dirty tire to a clean, high-tech raw material is complete. And now, let's jump to the place where this black crumb will find its true calling: the construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. This isn't just a green carpet. It's a backing with long, soft polyethylene blades sticking straight up. But for now, they look sad and limp, pressed against the base. For them to stand up and look like real grass, they need support. And this is where a special machine, looking like a large fertilizer spreader, drives onto the field. A process called infill begins. First, the machine spreads a uniform layer of fine, rounded quartz sand over the entire field. It's heavy and settles right at the base of the carpet, acting as ballast to keep the turf from shifting and helping to stabilize the blades. And following the sand, our main hero is spread onto the field, the black crumb rubber. The machine distributes it just as evenly over the entire surface, and here, the main transformation happens. This crumb fills the space between the blades, forcing them to stand vertically, just like real grass. Secondly, and most importantly, it creates a cushioning layer. When an athlete runs, jumps, or falls, this layer of billions of tiny, springy rubber particles compresses, absorbing the impact energy. It's like running on a billion tiny trampolines. This drastically reduces the strain on athletes' joints and makes falls much safer. The final touch is combing the field. A special machine with a huge brush drives over the turf, thoroughly mixing the sand and crumb rubber and brushing them deep down to the base, making every blade stand perfectly straight. And so, when the work is done, what stands before us is a perfectly green, resilient, and safe field. And none of the players running on it might ever guess that under their feet, between the bright green blades, lie millions of particles of old car tires that have completed their epic journey from the roar of the motorway to the quiet, springy surface of a sports arena, having received a second, much nobler life. To create one standard American football or soccer field, you need, on average, between 20,000 to 40,000 old passenger car tires. Just think about it. A single field completely eats up a whole mountain of rubber waste. And how many of these fields are there in the country? Right now, there are over 13,000 artificial turf fields in the US, at schools, colleges, parks, and professional arenas. And that number is growing every year. Now for some simple maths, even if we take the minimum figure of 20,000 tires per field, it turns out that over 260 million old tires have found their new home in the surfaces of sports fields across the country. That's almost a year's supply of all the rubber scrap the country generates. Natural grass is a very fussy thing. It needs to be constantly mowed, watered, fertilized, and given time to rest. On average, a natural field can handle no more than 20 hours of play per week. And an artificial turf field, it can operate 24 hours a day, 7 days a week, in rain or shine. Now, let's talk about water. A single artificial turf field can save from 500,000 to 1 million gallons of water every year. That's the amount of water an average family uses in several years. Add to that the savings on fertilizers, pesticides, and lawnmower work, and the benefit becomes obvious. So next time you see a bright green field, know that it's not just a place to play. It's a monument to human ingenuity that solves a waste problem, makes sports safer, and saves precious natural resources, one old tread at a time. Imagine a magnet so powerful it can lift a weight 1,000 times its own. How can a piece of metal stop a jet engine turbine or become the heart of a Tesla electric motor? The secret lies in rare earth elements, materials that hide more mysteries than gold or platinum. To create a single neodymium magnet, you have to move mountains of ore, melt metal at over 2,700 degrees, and use technologies that resemble alchemy. But there's a detail that almost no one knows about. Watch till the end, and you'll learn a secret that will change your understanding of the power of metal. The mining and initial processing of rare earth ores are a key stage in the production of neodymium magnets, as this is where the foundations for obtaining the necessary components are laid. This process begins with the large-scale mining of ore, containing the rare earth elements that make up neodymium. In the first stage, the ore is extracted from the earth using various mining methods. This can be either open-pit mining or underground mining, depending on the depth and type of the deposit. After extraction, large chunks of ore are delivered to crushing plants. At the crushing plants, the ore undergoes primary crushing. Large boulders of ore pass through a series of crushers that gradually reduce their size into smaller fractions. This is necessary for further effective processing and extraction of valuable components. The crushed ore may then be fed into mills for further fine grinding into a powder or a pulp, which consists of fine ore particles suspended in water. The next critically important stage is ore enrichment, the purpose of which is to separate the rare earth minerals from the waste rock. This process can involve various methods. One of the most common methods involves mixing the crushed ore with water and special reagents. These reagents selectively attach to the surface of the rare earth minerals, making them water repellent. Air is bubbled through the mixture, creating bubbles to which the hydrophobic minerals adhere and rise to the surface, forming a froth that is then collected. Heavier particles settle faster, allowing them to be separated from the lighter ones. Some rare earth minerals have magnetic properties, which allows them to be separated from non-magnetic components using magnetic separators. After enrichment, a concentrate is obtained, which contains a much higher concentration of rare earth elements. However, this concentrate is still not a pure metal. It requires further chemical processing, which usually includes dissolving the valuable components with acids or alkalis, precipitation, solvent extraction, and ion exchange chromatography. These processes allow for the separation of each rare earth element individually and its purification to a high degree. For example, neodymium is separated from other rare earth elements like praseodymium or samarium. The final result of this complex chain of processes is the production of high-purity neodymium oxide, which is then reduced to metallic neodymium. This metallic neodymium, in the form of granules or ingots, is ready for the next stage, alloying with other components to create powerful neodymium magnets. The entire process requires strict quality control and significant energy expenditure, but is absolutely necessary to obtain the raw material for the production of these strategically important materials. After the careful extraction and purification of rare earth elements, particularly neodymium, comes one of the most crucial stages in the production of high-performance neodymium magnets: alloying. This process demands extreme precision and control, as the final microstructure and, consequently, the magnetic properties of the finished material depend on it. The purified metals, neodymium, iron, and boron, are carefully weighed in strict proportions. These three elements are the main components of the alloy, providing its unique magnetic characteristics. In addition to them, small amounts of other elements, such as dysprosium, terbium, cobalt, or copper, may be added to the alloy. These additives are introduced to achieve specific properties, for instance, to increase the magnet's temperature stability, improve its resistance to demagnetization, or modify the material's brittleness. The exact composition of the alloy is a trade secret for many manufacturers and varies depending on the desired final characteristics of the magnet. The weighed components are placed in a specialized vacuum induction furnace. The use of a vacuum is critically important as it prevents the oxidation of the rare earth metals and other components at high temperatures. Oxidation would lead to the formation of undesirable phases, which would degrade the magnetic properties of the material. Induction heating ensures rapid and uniform melting of all components, creating a homogeneous melt. The melting temperature in such a furnace can reach over 2,700 degrees Fahrenheit. After achieving a complete melt and homogenization of the alloy, the stage of rapid cooling, known as the strip casting method, begins. This is a key moment for forming the optimal microstructure. The molten metal is poured in a thin stream onto a rapidly rotating, cooled drum. Contact with the cold surface of the drum leads to an extremely rapid cooling of the melt at a rate of up to millions of degrees per second. This extremely rapid cooling prevents the formation of large crystal grains and allows for the formation of an amorphous or microcrystalline structure. Instead of the typical crystalline structures formed during slow cooling, extremely fine grains are formed. This process is also known as rapid solidification, and it is fundamental to achieving high magnetic properties. The resulting material takes the form of thin, easily crumbled flakes or ribbons. This unique microstructure, with very fine, often anisotropic grains, is the key to the high strength of neodymium magnets. The smaller the grain size, the more difficult it is for the magnetic domains to change their orientation, which provides high resistance to external demagnetizing fields. Thus, the alloying and rapid cooling stage is fundamental for forming the magnetic characteristics that will later be locked in during subsequent production stages. After the alloying and rapid cooling stage, when thin flakes or ribbons of the neodymium iron-boron alloy have been formed, a stage called hydrogen decrepitation begins. Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage: liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies.